Good afternoon. So it's a long title. I will start by explaining what variable automata are. Then I'll explain a little bit about the canonical form that we have for them, and then I'll move on to learning. So let me start by describing variable automata. So these are finite automata in which the letters are interpreted as variables over some infinite domain. So let's look at this example. It has, as you see, an alphabet of size 3. It has x1, x2, and y. And we call x1 and x2 bound variables. And the meaning is that they get the same assignment throughout the run. And y is a free variable. We can treat it as a joker. You can get any variable. So let's look at an example run on this automaton. So let's say we run on this word. Okay, so this word we call a pattern word because it only consists of the variables. And the concrete words that we get from this automaton is by assigning variables to the, assigning values to the variables. So the rules are that every concrete word consists of a pattern word in which all bound variables are assigned the same value. So in this case, x1 is assigned 2, and x2 is assigned 4. And the y variables are freely assigned. So in this case, it can be 8 and 3, and they all have to be different from each other. So every assignment to y has to be different from the x variables, and they have to be different from each other. And essentially, if you know a little bit about register automata, it's like a sort of a fraction of register automata with limited rules. Okay. So obviously, you can get many concrete words from every pattern word, and we call the set of all concrete words from a pattern word the language of the pattern word. And the language of the automaton is the set of all concrete words that we get from all pattern words. Okay. Now, what we can do with these automata is we can model infinite state systems in which the control is finite, and the source of infinity comes from the data. So we can have a very simple example of send and receive a communication protocol, and this automaton, since x must get the same variable, this automaton sort of says that when we send some message with content or ID x, some sort of data value, then eventually we get the receive with the same value. So the x variable, since it's bound, it has to get the same value. And otherwise, we can have different messages with different IDs. And on top of modeling such systems, we can also model specifications for such systems with the automata. So that's the motivation for using them, and we use them in several such algorithms. Okay, so now I will talk about a deterministic fragment of these automata. So as usual, we describe deterministic automata as automata that have a single run on every concrete word. Now, in this case, having the underlying automaton deterministic is not enough. So let's look at this simple example. So as a deterministic finite automaton, this is deterministic. However, we have a run on this word, pattern word, and a run on this pattern word, and these two pattern words can produce the same concrete word. So this automaton is not deterministic. This automaton, however, is deterministic because the first value has to be assigned to x1, and then the rest of the values have no choice but to be assigned to y. Okay, so this is an example of a deterministic variable automaton. Okay, in this case, it's the language of this automaton is all words in which the first letter occurs again at some point in the run. Right, so we have the first transition and the second transition. All right, so we have a result from long ago that says that deterministic VFA are strictly weaker than VFA. And we call L deterministic if it has a DVFA, a deterministic variable finite automata that describes it. Okay, now, despite the fact that it is not enough for the underlying automaton to be deterministic, it's not hard to determine whether an automaton is deterministic. So I will not go into that. All right, so deterministic variable automata have very nice properties. They are the emptiness, universality, membership, and inclusion problems for them are all decidable and pretty easy. They are closed under the Boolean operations, and this does not hold for the non-deterministic case. So it makes sense to concentrate on them. And the contribution in this paper is an offering of a canonical form for DVFA, much like regular languages, and as a result, a learning algorithm for DVFA. So I will describe both these parts. All right, so I'll start with the canonical form. So let's say the pattern alphabet has k bound variables, variable y, and also constants, which I will ignore, okay, because they're less important. So first we define when a pattern word is ordered. So a pattern word is ordered if the bound variables occur in the order of their indices. So x1 occurs first, x2 occurs second, and then only after all the bound variables occur, y occurs. And now we can take a concrete word and assign it an ordered word. So it's very easy to do. We just take the first occurrence of a value and assign it to x1, and then the second occurrence and assign it to x2, and all the rest of the occurrences are assigned to y. So in this case, 2 occurs first, so it will be assigned to x1, and so on. So in this case, we take a concrete word and produce a pattern word for it. And the advantage of the ordering is that every word has a single ordering. And now we can define ordered DVFA, and these are DVFA that have runs on all ordered pattern words. And we can prove that every deterministic variable finite automaton with k variables has an equivalent DVFA in which all the pattern words are ordered. So that will help us with the canonical form. And it's quite easy to do. We just rename variables along the different paths, and sometimes we need to remember the assignment. So it actually has an exponential blow-up, but it's not a hard construction. And now we are going to define an equivalence relation over pattern words that will sort of mimic the Myhill-narrowed one for a finite automata. So we have two pattern words, U1 and U2. And we'll say they are equivalent under a pattern alphabet and a language L if the following holds. For every pattern word that we concatenate to U1 and U2, either both of the languages are included in L, or both of the languages are disjoint from L. And it's quite easy to see that it's an equivalence relation. And let's look at an example. So let's look at the language of all words in which the first letter is equal to the last letter. This is a deterministic language. So let's take k equals 1, meaning one bound variable. The two words x1, yy, and x1y are equivalent because they fulfill the property. If we concatenate any word that ends with x1, they will both be in the language. If we concatenate any word that ends with y, they will both be outside the language. Every concretization that we can produce. Okay, here's another example. In this case, both pattern words, the language, are included in the language. The first and the last letter are both in the language, are the same. Okay. And finally, these two words are not in the relation because the first pattern word, the first and the last letter are the same. First and second letters are not the same, and this will remain no matter what we concatenate to them. Okay. And since this is an equivalence relation, we can form the equivalence classes. So in this case, we have an equivalence class for the empty word. We have an equivalence class for all the pattern words whose first and last letters are the same for all concretizations. We have a single letter, and we have the complement language in which the first and last letters are not the same. And now we can prove that a language is deterministic, has a deterministic variable finite automata, if and only if there are finally many classes in the equivalence relation. So this is very similar to the Myhill-narrowed construction for regular languages. And I will skip the first direction. We only have to say that in an ordered DVFA, the number of states is greater or equal to the number of equivalence classes. And for the other direction, just like for finite automata, we use the equivalence classes. So let's look at the equivalence classes for the example language. So every equivalence class will be a state. The initial state will be the equivalence class of the empty word. There's a transition from one state to another, labeled, which leads by the concatenation of the equivalence class with a variable. So there's a transition labeled 1 from the equivalence class of x1 to the equivalence class of x1 and y. And the accepting states are the ones are the pattern words or the equivalence classes in which the language is included in the language that we want to accept. So in this case, this is the automaton that we get. And we can show that for a minimal number of variables, this is a minimal ordered deterministic variable automata for the language. And it's also possible, given an ordered DVFA, to minimize the number of variables that it uses. Okay, so that was the canonical form, and now we want to learn it. Okay, so in a learning algorithm, we want to construct a DVFA based on queries that we submit to some oracle. And there are many motivations for such algorithms. They're useful for model checking. We can use them to learn specifications of behaviors of infinite state systems. So that will be helpful. And we will be basing our algorithm on the Lstar algorithm for regular languages. So I will tell you a little bit about that. So basically, the goal is to learn an automaton. We have two entities in the algorithm. We have a learner who wants to learn a deterministic variable automaton, in our case. And we have a teacher who can answer several questions, so several types of questions. So the first type of question are membership queries. The learner can ask the teacher whether a given word is in the language or not, and the teacher will answer yes or no. And the learner keeps asking these questions until he has a stable automaton that he wants to inquire whether this is the one for the language, and then he can submit an equivalence query. Now, in this case, we can only ask about concrete words. So in an equivalence query, the learner asks the teacher whether this automaton that he has constructed is the correct automaton for the language, and the teacher can answer no and give a counterexample for a word that is in the language but is not accepted, or the other way around. Or the teacher can say, yes, that's the automaton for the language, and we are done. Now, in our case, for regular languages, the alphabet is known in advance. In our case, we don't even know the pattern alphabet, so we need to learn that as well. So in this scenario, we don't know in advance how many bound variables we have to use to express the language, so we will need to learn that as well. So the goal is to find a minimal ordered deterministic variable automaton for the language with minimally very many variables. Now, in real life, if you know the Lstar algorithm, the learner, in fact, keeps a set, or a single table. In our case, it will be a set of tables, and I will describe the content of the tables. So this is what a single table looks like. So the ith table is for a restricted pattern alphabet x1 to xi, and the other variables, and the other, constants in the language, which I will skip. And every, in the rows, we have an upper section, lower section. In the upper section, we have ordered words that use x1 to xy, and also in the lower section. In the rows, we have a pattern word, and in the algorithm, every pattern word is assigned a single concrete word. So this is both for the rows and the columns. And we do it in such a way that the concatenation of every row with column is still ordered. And the table entries are truth values. The truth value is 1 if the concatenation of the concrete word of S, the concrete word of E in this case, is in the language, and 0 if vice versa. Okay, so the way to fill the table is by using membership queries. So we fill all the tables. And finally, we can use the tables, just like in the Lstar algorithm, to construct an automaton. So every row we can look at it as a vector of bits, of zeros and ones, and these will form our states. So every row in the upper part corresponds to a state. And in this case, we also add the index of the table. And the transitions are, if this is a row for x, if we concatenate alpha, we get another row, so we have a transition labeled alpha from one state to the other. Now, to form a legal DVFA, the tables have to fulfill certain properties. So we can do that and get a legal ordered DVFA. So this is equivalent to the Lstar. We call the table consistent if for two identical rows we reach the same state by reading the same letter. So S1 and S2 have the same rows, and so we require that if we read some alpha from S1 and S2, we reach the same row. Okay, so in this case, this is an example of consistency. Okay, so 0, 1, 0, reading alpha, we reach 0, 1, 1 for both cases. Okay, so consistency essentially means determinism. And if the table is inconsistent, we can add columns to distinguish between the rows in case they are not the same. And the table is closed if for every state S, there is continuous states for every variable. Okay? So in this case, S1 reads alpha, we reach 0, 1, 1. So we want 0, 1, 1 to appear in the upper part. That's the part that determines the states. So a closed table basically means a full automaton. Okay, sorry. And if the table is not closed, we simply add the missing rows and then fill the table accordingly. And now we define, a table is refined. This is not for regular languages. This is for our case of variables. Table is refined if for every concatenation of row and column, we get the same result. So let's look at this example. We have x1 on the rows and yy on the columns. We have x1, yy. The concrete word that we assigned was ABC, and that's not in the language. And in the second row, we have x1, y, and in the column, we have y. So the concatenation is the same, x1, yy. And in this case, the concrete word that the algorithm assigned is ABB, and that is in the language. So we have inconsistency for x1, yy in this case. Now, this means that we didn't use enough variables. So what we do in this stage in the algorithm, if the table is not refined, we simply add variables to distinguish between the two words. So in this case, we only use one bound variable, and if the result is not the same, means we have to use more variables. So we add a single variable in this case, and to distinguish between the two concrete words, ABC and ABB, that the algorithm maintained. All right, and then we have to start over. Yeah?
Maybe I'm missing something, but isn't the number of variables, bound variables, equal to the alphabet?
No, the alphabet, the concrete alphabet may be even infinite. Okay, we want to use the minimal number of variables to express the language that we want. So the first and last letters are the same. We only need two variables, one bound and one unbound, but we can express many, many different values. Okay, so once we have a table that fulfills all properties of closed, consistent, and refined, we can construct the DVFA as we have described earlier and submit an equivalence query. And if the teacher answers, no, that's not the algorithm, that's not the variable automaton that I had in mind, then we can update the tables and continue. We add the counterexample that the teacher returned and continue the algorithm. And otherwise, the teacher returned, yes, we are happy, we have found the automaton that we were seeking. Okay, so some properties of the algorithm. So let's say that T is the set of tables, AT is the DVFA that we construct according to these tables, and K is the number of variables that we have reached so far. So we can show that the automaton is a minimal ordered automaton for over this set of variables that is consistent with the table. We can also show that an ordered DVFA for the language has at least K bound variables, so we didn't add too many. And finally, we can show that any ordered DVFA with more than K bound variables is larger than the automaton that we construct. Now, along with the observation that every step of the algorithm, which we call Lstar, adds either one state or one variable, it means that we converge eventually to the minimal ordered DVFA with a minimal number of variables. So this is for the correctness of the algorithm, and now for the runtime. So checking whether the table is consistent, closed, and refined is not hard. It's enough to go over the table once and ask enough questions. And the number of iterations that we run for the algorithm is most the number of minimal variables that we need, because we start a new iteration of the algorithm, we reconstruct the tables only when we find that we need more variables, and we have already at least argued that this number of variables does not pass the minimal number of variables. So the conclusion is that the algorithm runs in polynomial time with respect to the size of the algorithm, of the automaton that we construct, the size of the alphabet, and the counterexamples that we get from the teacher. All right, so to summarize, we saw a canonical form for DVFA. So in general, languages over infinite alphabet are highly irregular. So finding fragments for which there is a canonical form is quite nice. So this canonical form enables a minimal and refined model for systems and specifications that we use for these automata. And we saw an efficient learning algorithm for the languages for these types of automata. As future work, we want to use this learning algorithm for the purposes of model checking. Mostly we want to use them for an assume guarantee sort of technique for model checking certain type of systems. And of course, we want to find more learnable fragments to enrich the languages that we can learn. So, thank you.